first. It's going to be recorded from now on. Let me share the slides. Okay, these are the slides. You should be able to see them right now. Okay, we have started to talk about binary search trees last time, right? Binary search trees are special binary trees, and we can define binary search tree recursively, as in here. We have already covered these, so I'm gonna go over them really fast. A binary search tree could be empty or has a root node with two subtrees where the elements in the left subtree are smaller than the root value and elements in the right subtree are larger. And of course, left subtree and right subtree are both binary search trees. So this is the recursive definition. Based on this recursive definition, this is a binary search tree, since for any node you can take, for example, that, everything in the left subtree are smaller than that, and everything on the right subtree are larger. You can check it out for all the nodes, and you can see it. You can see this property here. Okay, this is the algorithm for search operation we have seen. Actually, the search operation is performed using this recursive definition. We start from the root. We always start from the root, since we have the reference to root only, and based on the search key value and the value at the root, we continue the search operation with the left subtree or right subtree, right? So how we continue, since both subtrees are binary search trees, we can search the search key on the left subtree or right subtree recursively, right? We perform the operation recursively on one of them based on the comparison of the key with lay. If the key value is the search value is less than lay, we have to continue with the last subtree. If the search value, the key value, is larger than lay, we have to continue with the right subtree, and the value could be on the right subtree only, since everything on the left subtree are smaller than the lay and in turn smaller than the key value, right? So we continue with one of the subtrees. If we found it on the root, if the search key value is lay, we found the value. This is one of these base cases, and if the tree is empty, we can decide that the value is not in the tree, since the tree is empty, right? So the algorithm is here. We have seen this algorithm before. We have a base case for root equal to null, and base case if when they are equal. In both cases, we don't have any recursive call, but if the target is less than the value, we search on the left subtree, and if it is larger, then the search operation continues with the right subtree. Okay, for example, to be able to search capped, we compare with lay, and since capped is smaller, we continue with the left subtree, and we compare with house. Since it is larger, we continue with the right subtree. Since it is larger than Jack as well, we continue with the right subtree. Since it is smaller than killed, we continue with the left subtree. And there we see that they are equal, so we found the value kept. The performance depends on this, the height of the tree, and height of the tree is in the best case logarithmic, and the best the best height for its height, the best case is logarithmic theta log n. The worst case height is linear, right? Because of that, the running time of the search operation, the best case for n values is constant time, since we can find it on the root, right? We can search for lay as well. And the worst case running time is ON. If we actually theta n, we can say theta n. If the tree is something like this, and we search for the element in at the leaf, there is only one leaf, and if we search that leaf, it takes theta n time. So the running time of this operation is ON, but this ON is only possible when this kind of tree happens. This is not always possible, and in general, for the trees like this, in this slide, we get the running time to be log n. So that's why we say that searching a tree in general is log n. Actually, average running time is logarithmic, we can say. Okay, we also talk about this search tree interface. We have add method to add a new item, check whether the target is available or not using contains method. Find performs the same thing but returns the element or null. Delete deletes the element and returns it. Remove just removes it and returns a Boolean value whether the operation is successful or not. So this true operation and this true operation are very similar, but we can say that we have three basic operations: to add a new item, to delete an item, and to check an item is available or not, right? In search tree interface. This is how a binary search tree class can be implemented. It is a generic class, as you see, and this generic class, binary search tree, implements the search tree interface and extends the binary tree. Binary tree in terms, as you remember, has a binary tree node, which is, as you see from here, it is an internal class, and it keeps a reference to a node, which is the root node, right? And binary tree has the data and true references to itself, right? We all know that. So for this binary search tree, we are gonna see that we will use add return and delete return to data fields. It's not a good way to do it, but it is the way the writer of this textbook prefers. We are going to talk about it in a minute. This is the find operation. We have talked about this find operation since the find operation in the interface cannot be performed recursively. We just delegate the operation to a private find operation, which takes a root node and the target value as parameters. And this operation is recursive. As you see, it calls itself and implements the algorithm that we have seen a couple of minutes ago. This algorithm is implemented by this private find method. And one-to-one implementation, if the local root is null, return null, otherwise compare target with the data at the local root. If they are the same, return the data. If it is smaller, continue with the left subtree. Otherwise, continue with the right subtree by recursive calls, as you see. One-to-one correspondence with the algorithm, right? So we have already analyzed this method, so we can continue with the next method, insertion operation. Actually, when we have to insert a new value in the binary search tree, we perform an operation similar to search operation. And when we find that the element cannot be found, it is not found, we decide the element is not found in this algorithm when we get to a null node, which means we continue search operation until we find that this is not in the tree. The insertion of ill is shown here. To be able to insert ill, we check with lay and continue with left subtree, control with house, right subtree, jack, right subtree, killed, left subtree, kept. It should be on the left subtree, and there is no left subtree, as you see here, actually, in this thing, since left subtree is null here. We decide that ill is not in the tree, and when we find that, we can insert it as a left subtree for the cat. So insertion operation is very similar to find operation. You see the algorithm here. It's very similar. At least these true recursive calls are almost same. If the item is equal to root data, in that case, for example, if you try to insert rat into this tree again, we compare rat with lay and decide on to insert on the right subtree. Then, while inserting on the right subtree, we compare with rat rat is equal to rat, and we see that rat is in the tree. Now we can say that we cannot insert the rat again. It is already in the tree, and we return false. Since we cannot insert the same value twice in the binary search tree, if an element already in the tree is tried to be inserted, the algorithm returns false. Okay, and if the root is null, which means while inserting ill, we come to this point where left subtree of the capped is null, and there we perform this operation. Left subtree of the capped is null, and that subtree is replaced by a tree with just one node. Replace the empty tree with a new tree with item at the root. So we replace the left subtree of capped with a tree with just one node that contains ill, and return true since ill is successfully inserted in the tree. Okay. So then we have to insert another one. For example, if we try to insert what me has to be compared with lay, and we decide that it should be inserted on the right subtree, right? We compare with the rat, and we decide that it should be inserted on the left subtree. And me and milk is compared. Me is smaller than milk, so we continue with the left subtree again. When we compare malt with me, malt is smaller than me, so we have to insert on the right subtree. Man and me, man is smaller, so we have to insert on the right subtree. And married is again smaller than me, so we have to insert on the left subtree of married, right subtree of married, but the right subtree is null, so we create a new tree here with one node only, and it has me in it. This tree is created, and it is made to be right subtree of married. So the new tree will be like this. As you see, we always insert as a leaf node, and we insert when we make sure that the element is not in the tree. When we reach to a, a position where the element is not in. For example, we come to this point that the right subtree of crowd is empty, and insert there. What can be inserted in this position? To be inserted in this position, the value x to be inserted here should be greater than, not less than, greater than crowd, right? Also, it is on the left subtree of crumbled, so it should be less than crumbled, right? Anything in between crowd and crumbled will be inserted in this position. You can check any position, for example, to be able to insert in this position as a left subtree of the. Any y value in this position should be less than the, right? And it should be less than this, less than toast, of course, as well. And it should be greater than that. So anything greater than that and less than the will be inserted in this position as a left subtree of the. So for each value has a specific position that the value is can be inserted. For example, anything less than all is inserted here. Anything between all and will be inserted here. Anything between and 8 is inserted here. Anything between 8 and build is inserted here. Build and cat will be inserted here. Cat and cook, cook and corn, corn and cow, cow and crowd, crowd and crumbled, crumbled and dog, dog and farmer, farmer and fallen, fallen and horn, horn and house, etc. As you see, any value can be inserted in just one place. Okay, so we in this algorithm we find that unique place and insert the new item in that position. Again, the number of recursive operations will depend on the height of the tree, and height is between logarithmic to linear, right? And the tree could be something like this, and we could be inserting this in this position, right? Although this is the worst tree with linear height, inserting as a left subtree in this root node is constant time. So the best case running time of this algorithm is constant time again. Worst case running time will be inserting in this position, which is linear time. But in general, this kind of tree happens very rarely. That's why the height is logarithmic in many cases. And that's why the average running time will be logarithmic. Okay. How can we implement that? Again, implementing this public method recursively is not possible, since when we call with item, we cannot make the problem smaller and smaller throughout the recursive calls. So we have a helper method add with two parameters. One is root and the other one is the item passed, the parameter to be inserted. Okay. We have a precondition where the elements should be comparable, as you see. So the elements should be inserted, it should be comparable. Parameter is the item to be inserted, and the return value is true if the item is inserted, or false if it is already in the tree and it's not inserted in the tree, right? Again, of course, it's been inserted, but it's not inserted again since it is in a tree already. So this add method, recursively implemented add method, has a return value different than the public add method. Public add method returns true or false, but recursive method returns the new local root after the insertion. So after insertion, the tree is changed probably if the insertion is successful, and the new local root is returned by this recursive method. Local root is parameter, the first parameter. As you see, the insertion will be done if the local root is this, the insertion will be done in this tree. And of course, the item is going to be inserted, right? Local root is the reference of the root node of the tree we have in our hand now. Of course, it is a part of the, it could be part of a larger tree, of course. We have completed the operations until the local root probably, right? So if the local root is null, this is not the case. In that, for the time being, let's assume that it's not null. We continue. If the value in this local root is equal to the item to be inserted, if the item and local root data are equal, compared to method returns 0, then we cannot insert the value again. So we just return the local root before the insertion, since we cannot insert again, but we change the value of a data field in the class, add return. So add return is defined here, as you see, or here. It's a data field, a protected Boolean value, and we set this value during the add operation, and this public add method will use it. So this private add method will set it, and public add method will use it and return this add return value. Why do we use such a external value that is defined in the class, because this add method, private add method, returns not a Boolean value, but the local root. And actually, this add method should return two values. One is this local root value, and another one is whether the add operation is successful or not. Two values has to be returned. The writers of the book prefers that returning local root is done by return value of the add method, but returning the other value, whether the add operation is successful or not, by using a data field add return. So the algorithm, the method sets this value to be true if the item is added, and it sets it to be false if the item is already in the tree. So this is a side effect of this private add method. Side effect, it changes the environment. It doesn't return something only, it returns something, of course, and it performs some more operation on the top of it, and it sets some value some value defined in the class, some variable actually defined in the class, data field in the class. That is not a nice way of performing the operation. We could do other ways. We could use other ways. For example, we can pass another reference here for add return and set the parameter in that reference as well. So this kind of class data field can be used, of course, but it's not a good idea. Why the writers of the book prefers that, I don't know, but it's not a good way to do it. The better way is to use some other parameter here to return add return. We can add a third parameter and we can return the value true or false in that third parameter. Of course, the add return cannot be a basic type, since basic types are passed as value in Java. It should be class type, right? That contains Boolean value can be used. Okay. Anyway, the writers of the book prefer to use add return. As I said, add return is a class data field. Add return is set by this add method, recursive add method, and used by this public add method to return whether the add operation is successful or not. I hope it's clear now. It's better not to use that kind of data field, but used in the book, so I will explain it like that. Okay, so here when the item and the local roots data are same, we cannot insert the same value again, So we set a return to be false and return local root. Otherwise, if the item is smaller, we continue with the left subtree of the local root and insert this item onto left subtree. Since the add operation will alter this the left subtree, for example, left subtree of this local root is going to be altered, changed, modified by the add method, since it's going to insert a new value in. This add method will return the new tree, and it's going to be set the left subtree of the local root. Okay, the add method will return the new local root and new left subtree of the local root, and it's going to be set as a left subtree of the local root. Okay, and local root is returned afterwards, since the add method should return the new tree, right? Result in new tree. The same for the case when the item is larger than the data at the local root. In that case, we continue with the right subtree, insert the item into right subtree using add method, and the add method will return the new, after modification, after insertion, the new subtree. So that subtree has to be assigned as right subtree of the local root, and local root is returned again for the right subtree. So these are general cases when the local root is not null. If we continue with the left, right, left, left, for example, and right, and there we make a call for this last subtree, which is null. This case happens, right? And since the local root is null, we decide that the element to be inserted cannot be in the tree. So we make add return to be true, that we are going to insert the value. Create a new node, one node tree, create a one node tree. Item is inside the tree, right? As the data in the tree, in the node, and return this one node tree. This tree is returned, as you see. Since we call this for the left of, we called this add method where the local root is null in here, right? As a left subtree. Left subtree is null. Item is inserted. Since it's null, a new node is created and returned. Now, the return value of this is this tree, and that's made to be left subtree, right? This connection is made over there. So the new node is connected to original tree by the calling. So when we create a new node, we do not connect it to the tree, but the calling of this method here gets that node and make it to the last subtree. Okay? And return. This is returned. This is called as right subtree, as you see. So in here, the return value is this tree, and it's made to be right subtree, etc., etc. Actually, we do not need to perform this, traverse these recursive calls. It is good to do it sometimes, but it's not necessary to see that the algorithm is correct. How do we check the algorithm is correct? First, we check the base cases. If the local root is null, after insertion, if there is nothing as a local root after insertion, we have a one node tree, right? So this base case is correct. If the element is equal to local root data, we cannot insert the element. So we have something like this, and the data at the local root is equal to the inserted item. So we do not have to do anything, just return false and return this subtree local root, local root as a return value. That's also correct. This part is correct. And if the add operation is performed correctly by this recursive call, so let's say we have a larger tree, but we come to this position, and since we have to insert on the left subtree, the insertion at the last subtree is performed perfectly by this recursive call. Then making on as a last subtree of the local root is the correct way of doing it. So this part and this part is similarly are correct, and we can see that the algorithm is correct without checking, without traversing the recursive calls, of course. Okay, any question so far? So this non-recursive add method will depend on the running time. The running time of this method is depend on the running time of the recursive one. So this algorithm takes, in the best case, constant time, in the worst case, linear time, right? But we expect it to be logarithmic in general. Because of this add method we have covered before. Any questions so far? Okay. The last operation is removal. As I said, the interface contains the search operation, add operation, and delete operation, right? We have already covered this and this. The last thing is to delete an element in the tree. And when you look at this tree, if the element to be deleted is not in the tree, for example, here, if we try to delete me, it is on the right, left, left, right, right, right. Here we see that me is not in the tree, and we can decide that we cannot delete it. Delete is unsuccessful, right? We cannot delete me. But if we have to delete, for example, um, what? Farmer. Farmer, when we compare with lay, it has to be deleted from the left subtree. Since it can be on the left subtree only, it cannot be on the right subtree, right? When we compare with house, it has to be on the left subtree. And we compare with cow, farmer is large, bigger than cow, so it has to be on the right subtree, right? Then it is bigger than dog, it has to be on the right subtree. Smaller than fallen, so it has to be on the left subtree. And when we compare farmer with farmer, we found that found the farmer in the tree, and as you see, there is no child for farmer. So as we insert farmer as a leaf, deleting farmer as a leaf is very simple. We take this out and make left subtree of fallen null, then deletion is completed, right? If the element to be deleted has no children, then deletion is simple. But that's not always the case, right? For example, we may need to delete priest. Of course, we have to start with lay, go left, right, left, and come to priest. To be able to delete priest, it has just one child. That's also a special case. If there is only one child of the node, deletion again simpler. How? Since milk has priest as a right child and priest has only one child, making this one child as the left child of milk is sufficient to delete priest. Priest is not now deleted. Milk has a left child of malt. Milk has a right child of mourn. And we are done. What if a node that has two children has to be deleted? For example, this that. That needs to be deleted. What can we do? Then we have to replace this position with another value. Remember, that is between any value here and any value on the right subtree, right? Taking any value on the right subtree and putting in a place of that doesn't solve the problem. We have to pick a special value. If we have to replace that, we have to find the smallest value on the right subtree or largest value on the left subtree. Largest value on the left subtree is tethered, and smallest value on the right subtree is the. We can either replace this that with the or tethered. For example, let's say we decide to replace that with smallest value on the right subtree, the. We delete the here and make that to be the. Then deletion is completed. And it is easy to delete the since it doesn't have any child, right? If we decide to use tethered, for tethered to be largest of the left subtree, it shouldn't have any left child. So at least one child of the tethered should be null. As you remember from the case of deleting priests, it is easy when a value has one child, right? So deleting tethered is easy by making one child showing as a right child of shown. Tethered is deleted, and we can make tethered to be here. Okay. In either case, taking the smallest value on the right subtree or taking largest value on the left subtree and replacing the root value with that value is enough to delete a node with two children. So we have three cases for removal of a value in the binary search tree. If the item to be removed has no children, the case is simple. Delete it and make its parent to be null. Left subtree of right subtree of the parent to be null. If it has only one child, after deletion, that one child and it's, for example, it can be like this, right? This tree will be the result of deletion of this node in this larger tree. Deletion or after deletion, for example, this is TL. After deletion, the resulting subtree should be TL, right? Of course, if this is the right child for a node, this is gonna be right child of a node X, for example, right? So change the reference to this item so that it's reference to its only child. So this reference should be reference to its only child. That's simple. It is shown here. For example, we have is and in. To be able to delete is, we just make left subtree of Jack to be in, right? And to be able to delete house, there are two cases. We can replace it with the smallest value on the left subtree, which is horn, or largest value on the left subtree, which is horn, or smallest value on the left subtree, which is in, right? We can replace this house with horn or in. In this case, largest value on the left subtree is preferred, and horn is moved to in place of house. So if the item to be removed has two children, replace it with the largest item on the left subtree, which is in order predecessor. In order predecessor means the largest smallest value. Just the value just comes before the house, or just comes just after the house, which is in sorted order. Remember, when we traverse the binary search tree in order, we get a sorted sequence, right? We are gonna see the code in a minute. Let's have a break, and after the break, we are gonna continue with the implementation.